YouTube, this is my first video on a short module on proving trig identities, and so I'm going to go ahead and get straight into things and start with the difference between a conditional say statement and an identity statement before we start into proving trig identities. So know what an identity is. So to do this, what I want to do is kind of bring up the difference between two equations here. I could write, say I gave us an equation that said sine of theta equals 0, and I say this as opposed to say sine of x squared, not sine of x squared, but sine squared of x equals 1 minus cosine squared x, okay? So we're going to say this first statement here, just to let you know, is a conditional statement. And the reason why we say it's conditional is because it's only true for certain values of, say, in this case, theta. You know, we're dealing with an input theta. So for example, you know, if I said, well, sine of theta, this equals 0, where would this be true at? We could say like 0 degrees or 90 degrees or any multiple of pi. We say pi n, you know, if we're talking about radians. But that would make this true. It's not true for all things. Whereas when we look at an identity statement, okay? Identity statements happen to be true for no matter what you plug in for the independent variable. So for x here, you know, if we were to substitute in, say, like 30 degrees, and we get sine squared 30 degrees. I'm working in degrees because I think we'll be more comfortable with it this way. 1 minus cosine squared of 30 degrees. But the thing here is this, you know, like sine of 30 degrees in the first place is a half. So we get a half squared, and this would be equal to 1 minus now cosine squared of 30. That'd be cosine of 30 squared, which is radical 3 over 2 squared. But if you look at this, you know, you end up with a fourth on the left here, and on the right you get 1 minus, if you square the top and the bottom of this, you get 3/4. And so here's the deal. You get 1 minus 3/4 is a fourth. So you get a fourth equals a fourth. But the point here is this. When you talk about identities, we're talking about statements that the left and right sides are true no matter what you plug in for them. And so the reason why I wanted to mention this before we start is simply this. Since we are working with identities, that is, things are true on the left and the right, it's a little bit different from conditional statements. Remember, conditional statements, you could look at it as like some equation here, like sine of theta equals 0. The nice thing about conditional statements is you're allowed to do something like this. You're allowed to operate on both sides. I could add 1 to the left, and I could add 1 to the right, and I'd still get some statement that's true. We'd say, well, then sine theta plus 1 equals 0, if it's a conditional statement. Thing is, with identity statements, you are not allowed to do one side what you do to the other. We are simply stuck with what we have, okay? So that being said, we're going to go ahead and get into verifying trig identities, but essentially what you can look at here is I got a couple of trig identities where I say verify them. What we want to do is we want to show that the left side of this identity, like secant squared theta minus 1 over secant squared, is equal to the right side. And so in order to do this, what we're going to do is we're going to transform. We're going to transform one side, transform one of these sides into the other side. But what we're not allowed to do are things like let's subtract 1 from both sides, because remember, this is an identity statement, not a conditional statement. So what we're going to do is try to prove that one side equals the other side by transforming it into that side. And if you can get it to turn into that side, you're going to say, yeah, well, then they must have been the same to begin with. So before we go ahead and start verifying a couple of very simple identities, we're going to look at a few guidelines up here to follow. And this is true whenever we verify identities. We want to go kind of through this step process here. Step 1. We are going to work with one side of the equation at a time. And I give this little note here. It's often better to work with the more complicated side first. So for instance, in this identity down here, this first one, I say verify this identity, we would tend to work with the left-hand side if I've been given a choice. It's the more complicated of the two sides. Number 2 here says this: look for opportunities to factor an expression, or maybe if you're going to add fractions, find a common denominator, or square a binomial, or create a monomial divisor or denominator, okay? So essentially, we're going to use algebraic techniques to kind of simplify this left side into the right side. Number 3, look for opportunities to use the fundamental identities. These are things like this. If you see like a cosecant of, say, theta, we can easily rewrite that as 1 over sine theta by using simple, trig identity substitutions. Or if you see a sine squared, we can write this as 1 minus cosine squared of an angle. And the reason why is because we have the trig identity, this Pythagorean, sine squared plus cosine squared equals 1, okay? And then last but not least on this number 3 here, sines and cosines, we say they pair up well, as do secants and tangents and cosecants and cotangents, but because of our Pythagorean identities. Remember, if this Pythagorean identity holds true, then we have 2 other Pythagorean identities that follow, but essentially if I were to divide all of this by, say, sine squared, you know, as a matter of just playing around with it. Sine squared. This identity is already verified. We could say, well, then you get 1 plus cotangent squared equals, let's see, the reciprocal of sine is cosecant, so I get cosecant squared. So we say that cotangents and cosecants pair up well, as do tangents and secants. Okay, so knowing your trig identity is going to be really helpful here because we'll do trig substitutions as well as our algebra that we said we'd do in step 2. Last couple here, just real quick. Number 4, if the preceding guidelines don't help everything we've said so far, we're going to just take everything, turn it into sines and cosines. It's a helpful thing to do sometimes. And then number 5 is don't stop, man. Always try something. Try to rewrite something because eventually you'll get to something that'll allow us to lead the left side into the right side or the right side into the left side. Okay, so verifying an identity. Let's go ahead and start by taking a look at this first one right now. We are going to work with only one side at a time because it is an identity statement, not a conditional statement. So let's go ahead and take a look at this left side. So it says secant squared of theta minus 1 over secant squared of theta. We want to prove that this actually comes out to be a sine squared of theta. So what are some things we can do here? I'm going to point out a few that we can do, and we'll work with them both and show you that there's more than one way to get there. But I'm going to start with this. The fact is, whenever you have a monomial divisor, that means a one-term divisor, what you can do is you can split up the terms in the numerator over that denominator. So for example here, we could rewrite the left-hand side as the secant squared theta on the top left there over the denominator of secant squared theta. Now minus the 1 over secant squared of theta. And so looking at this, a couple things I notice here. First of all, we say secant squared over secant squared. Well, that's just 1. That's 1. And then we say, well, 1 over secant squared, what is the reciprocal of secant? We say secant is 1 over cosine, but likewise cosine is 1 over secant. This is just true from our trig identities, okay? So we could say 1 over secant squared is the same thing as cosine squared. So now I've gotten to this statement right here, and I want to prove that this equals sine squared. Well, the way we can do this is going back to our fundamental Pythagorean identity. Look, the bottom line is if sine squared plus cosine squared equals 1, then if I were to put this cosine squared on the right side, I get this identity right here. It's an altered form of my original identity, sine squared equals 1 minus cosine squared. And while we're at it, you could always say that cosine squared is also 1 minus sine squared. But whenever you see a 1 minus cosine squared, recognize this, memorize it, because you're allowed to substitute in a sine squared. So all of this right here on the left-hand side reduces down to a sine squared of theta, which is what we wanted to show it equaled on the right. So congratulations, you just verified your first identity. And all we had to do was show that the left-hand side actually comes out to equal the right-hand side. So now I want to keep this video as short as possible, but I wanted to show you a different way to look at this, okay? One other way to look at this is we could have rewritten this in terms of, like, say, sines and cosines. So on the left-hand side, again, I'm working with the left-hand side. We say secant squared on top could have been listed as 1 over cosine squared of theta. And this was minus 1. And this is all over now 1 over cosine squared. The reciprocal of cosine is secant, okay? So now when you divide by a fraction, you know, we could say the same thing you're doing is multiplying by the reciprocal. So what we could do is we could instead take the top, 1 over cosine squared minus 1, and take it times cosine squared over 1. Which, when you distribute this, you see that this cosine squared over 1 times 1 over cosine squared becomes 1, and we get minus cosine squared. And we still end up with this, which still, we know from our Pythagorean identity, is the same thing as sine squared. So we proved that the left-hand side does equal sine squared, which is the right-hand side, so we verified the identity. Okay, so let's try this again up here on the top. Let's take a look at a few things. We want to definitely work with the left-hand side of this. The reason why is because it tends to, well, it looks like the more complicated side here. We want to show that all of this on the left equals 1. So, working with this, let's go ahead and recognize a few things. First of all, the top, I gotta be honest with you, this is sticking out to me, but sine squared plus cosine squared totally equals 1. That is the definition of the Pythagorean identity. So one thing we could do is we could start by rewriting just a 1 on the top. Whenever you see a sine squared plus cosine squared of an angle, it's 1. And this is all over cosine squared of theta times the secant squared of theta, okay? So now the nice thing about having these two factors down here in the denominator and one thing up top is we could say, well, then this would have been the same thing as 1 over cosine squared of theta times 1 over secant squared of theta. Likewise, we could also say this, not multiplying straight across, but the reciprocal of cosine squared is secant squared. So this is all secant squared. And then all this over here, well, the reciprocal of secant squared is cosine squared. Okay, and we're trying to show, keep in mind that this equals 1 up here. Nice thing about multiplying these two things is that they're reciprocals of one another. So anything times its reciprocal happens to equal, that's right, 1. Of course, we could have multiplied this, straight across right here in the first place. We could have multiplied these down in the basement right now, and they were reciprocals, and they would come out to be 1. We could have had 1 over 1 equals 1. But we did prove that the left side does indeed equal the right side. So that is what we're setting out to do when we prove trig identities. On to the next video.